Okay.
Okay, so
Last lecture.
here, let me toss you a candy. Good catch. These are courtesy of the qubit seminar because I still haven't gotten to Crossville. Let me quickly finish up the Dirac bracket business. Now, let me get to my place here. Right, so the Dirac bracket so it's first of all the Poisson bracket. And then it's minus an integral d2z, d cubed z, sorry, d cubed w, and then it's the Poisson bracket of the first term with, it turns out it's only chi2. It's only the second constraint that has a Poisson bracket with A. Then we have C inverse, and since this is Z, and this is chi2, this is 2Z, comma 1W. And then we have the Poisson bracket with chi1 of W and T with pi k of y and t. So that's the Poisson, that's the Dirac bracket. Now the first Poisson bracket is kind of obvious. It's AI of xt and pk of say yt, although here it is yt actually. And this is a sum over j, an integral d cubed z, and it's partial ai of xt, partial pi k yt, partial a j of z, partial pi j of z, and then it's minus the other term, but in the other term, what we've got is we've got a pi here and an a there, so that vanishes. So it's minus 0. On the other hand, this first term is just Kronecker delta ij and delta cubed of x minus z. Over here, it's Kronecker kj delta cubed y minus z, and we're summing over j. So this is sum over j delta ij delta cubed x minus z delta jk delta cubed y minus z, and altogether this is delta ik delta cubed, oh, this is integrated, d cubed z, so there's no room to write that, but in any event, what you get is delta cubed x minus y, which is what you think. So the Poisson bracket just gives you the naive commutation relations. Last time we worked out C inverse, at least I hope we worked it out, 2z1w. This is anti-symmetric, and it's 1 over 4 pi z minus w. And of course, this is at equal times. The other two Poisson brackets are also pretty easy to work out. I think we did them last time. xt with chi2y Poisson is minus the x derivative of delta cubed of x minus y. By the way, the fingerprints of Dirac are just all this. Not only did he suggest that the quantum commutator was IH bar times the Poisson bracket, but he's also the guy who invented the use of the delta function. It's just amazing. Pi I of x and t, chi 1y Poisson, and this is partial xi with a plus sign of delta cubed x minus y. Okay, so we put all these things together, and I guess it's worth doing. So I'm going to call this thing T2. And I'm just going to say that this whole thing here is T2, and I'm not going to write out T2 again. I'm just going to fill in what the terms are. And as far as minus signs go, we've got one here. We've got one there. And so that's 2 minus signs gives us a plus sign. And what we've got is integral d cubed z, d cubed w, dxi delta cube of x minus z, 1 over 4 pi z minus w, and ddwk of delta cube w minus y. And I see I've got a couple of typos here, but they're not serious. Okay, so if you, I think in the interest of time, you guys can figure that out, right?
Sure. Yeah, there's that issue of the minus sign though last time. Is that resolved now?
What's that?
There's that issue of the minus sign last time. We had an extra minus sign.
The minus sign last time is that we forgot about the anti-symmetry of C.
Okay.
C being defined as well, C is a matrix of Poisson brackets, so it's anti-symmetric. C inverse is also anti-symmetric because the inverse of an anti-symmetric matrix is anti-symmetric. It's the minus sign of the it's all in the notes that are online.
Okay.
And these notes are in chapter 3, sections, I don't know, 5, 6, 7, something like that.
Sure.
Okay, this thing turns out to be partial xi, partial xk, 1 over 4 pi. Wow, that's a big typo. X minus y. Huge typo here. So I was focused on the minus signs and the so the notes on Poisson brackets, Dirac brackets, application of QED, it's the last part of chapter 3. And I forget, it might be, yeah, it's the part of chapter 3 that's, I guess it's just before the section on QED. Okay, so if that's T2, then what we have as the actual quantum commutator, it's I times the Dirac bracket, and so we have AI of x and t, pi k yt is I times AI xt pi k yt Dirac. And so this is the naive quantum commutator, delta ik, delta cubed x minus y, and then it's I times T2, which is I times partial 2 partial xi partial xk 1 over 4 pi x minus y. It's another typo. The other two, ai with aj vanishing commutator, pi I with pi k vanishing commutator. In the Hamiltonian, what we would do is we'd say, well, this is an integral d cubed x, pi dot a dot minus L. But a dot is transverse, and so pi dot a dot, it's only the transverse part of pi that contributes. So we can add a perp symbol, meaning just the perpendicular part. And pi perp is, well, it's just a dot. And I'm going fast because I wanted to get through a lot of stuff since this is the last lecture of the course. So what we get then is an integral d cubed x, and this is pi perp or pi transverse squared, and then we subtract these, well, I should have written down Lagrange, you know, the action density. So here, let me write L is a half a dot plus grad a0 squared minus a half curl a squared plus ji, ai, or ju, anu if you prefer Greek. Then when we subtract that, what we get is minus a half pi transverse plus grad a0 squared plus a half curl of a squared minus g dot a plus g0 a0. And we get a cancellation here, so this is d cubed x, so it's a half pi transverse squared. The cross product, or the dot product, I guess it is a cross product in a sense, vanishes because pi transverse is transverse. And then you have this minus a half grad a0 squared. Well, what we have is we have minus di fi0 together with the Coulomb gauge condition give us minus grad squared a0 equals j0, and so that means that this term, which is minus grad a0, minus a half grad a0 squared, I'm just going to write this as b squared over 2, because it's just the magnetic field. So it looks like that. And then this particular term is all right, how did I write this? All right, let me, here, I've got some space here, so I'm going to write it here. Integral d cubed x minus a half grad a0 squared is integral d cubed x a half a0 grad squared a0. On the other hand, grad squared a0 is minus j0, and so this is integral d cubed x minus a half a0 j0. So this cancels cancels half of this, and so what we finally get over here is that h is an integral d cubed x a half pi transverse squared plus a half, I'll just call it b squared, minus j dot a plus a half j0 a0. This is the Coulomb term. And so Vc is a half integral d cubed x a0 j0, which is also written as a half integral d cubed x d cubed y j0 x and t j0 y and t over 4 pi x minus y. So the electromagnetic field, the transverse electromagnetic field in the, here I'm going to use 4-vector notation for x now, is an integral d cubed p square root 2 pi cubed 2p0 sum over the two polarizations e to the I px e of p and s. This is a polarization vector, 3-vector, a annihilation operator ps plus the adjoint term minus I px e star ps a dagger ps. Okay, so that's the transverse electromagnetic field. The transverse conjugate momentum is the time derivative of that, and so that's minus I integral square root of p0 over 2 pi cubed 2 d cubed p, and then it's a sum of s, a sum over all these things, ditto minus ditto. Right. And the annihilation creation operator has the usual properties. Delta cubed of p minus q delta s s prime. And these operators automatically give you the transverse delta function as the commutator of a with pi. And the reason for that is that the sum over the two polarizations of EI of P and S, E K star of P and S is delta IK minus EI PK over P vector squared. By the way, these vectors satisfy P dot E of P and S is 0. And these are 3 vectors, but you can consider them as 4 vectors with vanishing time component. All right, so that's part 1 of what I wanted to say today. Part 2 is what I started to say last time, and this is in Weinberg's, here I'm basically following Weinberg's 413 to 418. And so we have the Hamiltonian here, and so we have some time-ordered product of some operators. It's a ratio of the operators e to the I, this action. Well, I haven't written down what the action is. Coulomb gauge condition, integrate over matter over gauge fields and matter fields divided by the same thing. And this SC is the action in the Coulomb gauge, which is half A dot squared minus, I'm just going to write it as P squared over 2, plus A dot J, and then plus any matter terms, d4 x, and then minus the integral V Coulomb dt. This delta is actually this thing that I wrote so casually is actually a product over all of space-time of a delta function of del dot A of x and t. So it's a that Coulomb gauge condition is something that was a sort of hyper Dirac, isn't it? It's an infinite product of delta functions. Now the trick is that you multiply top and bottom by something called f. F for fudge factor, and f is an integral e to the I over 2 integral grad A0 plus grad inverse Laplacian J0 squared d4 x and integrated over dA0. So now we bring the gauge field that we had, the gauge field A0 that we took such trouble to get rid of, we bring it back now as a mathematical trick, because when we put this in the upper and lower parts there, and let me just say what graphic del inverse is. Del inverse is actually minus 1 over 4 pi x minus y. So in other words, the del inverse of xy is just minus 1 over this quantity. Now this f, we can massage it a little bit, and first of all, if we expand this product, we have a grad, so that's grad squared with a minus sign when we integrate by parts. Maybe I'll do this in 2 steps. So this is integral a half grad A0 squared minus A0 J0 minus a half J0 inverse Laplacian J0 d4 of x dA0. So what's happened here is that we integrate by parts on this term and we get a grad squared with a minus sign. But grad squared times inverse grad squared is just 1, or the identity or functional identity. And so that just gives us an A0 J0 term. That's this term.
So this delta inverse is the Green's function for the Laplace equation or something?
Yeah, yeah.
Okay, cool.
Right. The inverse Laplacian is Green's function.
Yeah, you read it. Okay.
And so we get this, and what we're left over with is this thing squared, and this thing squared is Laplace grad Laplacian inverse J0, grad Laplacian inverse J0. You integrate this by parts and you get grad squared, so you have grad inverse J0, grad squared with a minus sign, Laplacian inverse J0, these two things cancel, so you have minus J0 Laplacian inverse J0, which is this term, and the 1/2 is there. So that's what we get, and then the point is that this term is the Coulomb term, but with a minus 1/2 I, and over here we have, when we multiply this by I, we have the Coulomb term, and so the Coulomb terms cancel. That's the whole point of the F trick. So the Coulomb terms cancel, and so what we get is, we get omega t O1 ON omega. We get that this is now an integral O1 ON e to the I S prime delta gauge condition dA d psi over the same thing basically. And now this S prime is an integral 1/2 A dot squared minus 1/2 B squared plus 1/2 grad A0 squared plus A dot J minus A0 J0, and then a matter term which I could have omitted and just mentioned parenthetically. Now, we've got this Coulomb gauge condition being enforced all the time by this rule, and so we can add to S prime another term, and I'm going to just do that directly. I'm going to add in del dot A dot A0. In other words, in this action, we can imagine that A is not transverse because we've got the transverse gauge condition making it transverse. And so then we can pop this in, which is just 0. And on the other hand, this thing is actually the same, of course, after integration by parts, as A0 dot grad, A dot grad A0. And, okay, so what do we have at this stage after we pop in this term? What we've got is that S prime becomes S, which is an integral of 1/2 A dot minus grad A0 squared minus B squared over 2 plus A dot J minus A0 J0 plus LM d4 of X. So in other words, we already had the square of this term, we already had the square of this term. The cross term is what we just added in because it's really 0 because of the Coulomb gauge condition. But the nice thing about this is that this is minus 1/4 FAB, FAB, or IK, IK. In other words, this is just the Maxwell action plus AB, JB plus LM D4 back. So this is the gauge invariant action. And so now,
can I ask you a quick question?
Yeah.
Regarding
okay,
you
earned yourself a qubit candy.
a qubit candy. Wow. Yeah. So
I didn't get to Costco, so I stole them from the qubit seminar. Yeah, what's your question?
okay, yeah. My question is I'm slightly spooked
Huh?
by I said I am slightly spooked by the fact that. Well, no, maybe not. never mind. I was going to say that the fact that we have the A0, J0 inside of the integral, but I guess that that's fine. Because... No, yeah, okay, so I guess that... okay, yeah, I want to say that, like, this... I want to say that the grad inverse of the J0, if I integrate that over all space...
So you're talking about...
Yeah.
You're talking about all of this stuff.
Yeah.
Is that right?
Yeah. I guess. Okay. So we pick
it's
up.
all okay.
Okay. Sure. Yeah. Okay. Yeah. Well. Okay. Well, maybe the term that I'm thinking of. What happened to the J, inverse Laplacian J? What happened to
this term?
Yeah. Did that term not just become J0 A0 or something? Or no? I mean, that was my original thought.
All right, hold on. Oh, no, this cancels the Coulomb term.
Oh, it cancels the Coulomb term.
Yeah,
I see.
this cancels this term.
Okay. Yeah, okay. I will buy it. But we're still, like, I guess, don't we need two? The Coulomb term has two integrals in it, right? We integrate over x and y.
Yeah.
Right? But then we have J0 inverse Laplacian J0 and only one integral.
No, there's an integral d cubed x, and this thing has another integration.
That thing has an integration in it. Okay,
yeah,
so,
because this is 1 over 4 pi x minus y with a minus sign.
okay, yeah, but at what point did we have an integral over y?
Well, all of these things are implicit integrations when you have I mean, this is a Green's function, right?
Yeah.
Multiplied by something, so there's an implicit integration here.
Oh, okay.
In other words...
Okay. Sure, okay.
All right.
Yeah, sure.
Okay. All right, so what we've got here then is a nice gauge invariant action. And so then, this thing here, which we were again writing as omega time order product, I'm just going to write it as O's, is then an integral O's e to the I gauge invariant action. And the only thing we've got left is the gauge condition, dA d psi, divided by e to the IS gauge condition dA d psi. And so what do we do now? What we can do now is we can say here we're integrating over, actually we're integrating over all gauge fields here, but we've got a gauge condition. And so what we can do is we can say, well, let's make a gauge transformation on the numerator and another one on the denominator. So what happens if we gauge transform everything? Well, we're assuming these are gauge invariant operators, so nothing happens. This is already gauge invariant. We're assuming that these measures here are gauge invariant. And by the way, that was something that was sloughed over by people for a while. And it was a guy named Fujikawa who pointed out that if you made an axial gauge transformation, in other words, e to the I theta gamma phi on psi, that this part of the measure wouldn't be conserved. And that's why, that's the root of the problem of anomalies. Anyway, but we're assuming these are gauge invariant. This is gauge. The only non-gauge invariant thing is there. So if we make a gauge transformation, what happens is that this just acquires an extra term. And this one also acquires an extra term. And this can be a different extra term because we can, well, I used a capital lambda for some reason. So. And this is just like you're doing an integration, you just decide that you're going to translate the integral, and since you're integrating over everything, it doesn't matter whether you change, this is just changing the order of integration in the numerator, changing the order of integration in the denominator, so it isn't any, there's no difference. Okay, now we have two choices. The first choice is to say, well, we're going to integrate over all gauge functions in the numerator, all gauge functions in the denominator, and what that does is it basically cancels out the gauge condition in both cases. And so what we get then is integral O's e to the is dA d psi over integral e to the is dA d psi. So that says that you can compute things if you integrate over all gauge fields. Now, the problem with that is some people don't like that. I think it's fine. Some people don't like it because if you're integrating over all gauge fields, well, this is an infinite space of fields, and so you've multiplied whatever this thing is, you multiply it by a factor of infinity, but it's the same factor down here, so they cancel. And if you think in terms of putting this theory on a lattice, well, then it cancels in a, one by one in an obvious way, and the thing is, perfectly fine. So it doesn't bother me at all. And in fact, in lattice gauge theory, the one does not fix the gauge at all. One chooses to do this, although one does all of this in Euclidean space-time because you're computing the partition function. And so in lattice gauge theory, one integrates over all gauge fields, although if you Wilsonize the theory, then it turns out to be compactified. The second choice is to fix the gauge, and here what you do is you multiply the numerator and the denominator by something, and by a gauge fixing term, and the term, let's see, I'm running out of board space, and we still have quite a bit of time left. So the factor I'm going to multiply by is e to the minus I alpha over 2, an integral of Laplacian of this gauge transformation, or this gauge function, say, d4 x. So I'm going to multiply top and bottom by that. Or actually, we're still at this stage. I haven't yet integrated over everything. So we're at this stage, and we multiply the numerator by this, and the denominator by the same thing, but with a prime. And if we do that, but then before we actually integrate over all lambdas, we do something. Namely, we do a shift. So we shift lambda so that Laplacian lambda goes to Laplacian, I keep writing lowercase and it's really uppercase. Laplacian lambda minus a dot 0. And so the exponential factor is e to the minus I alpha over 2 integral, and it's Laplacian lambda minus A0 dot squared d4x, although in the notes in the book I actually put in a minus sign here, but since it's squared it doesn't matter. And now what we do is we integrate over all lambda. And when we integrate over all lambda, the delta function, which is now, it's del dot A, but A has changed, A changes under a gauge transformation by grad lambda. So this is, so in other words, when we do, remember we had these gauge, this is what we had. We had divergence of A plus Laplacian lambda. So this thing, this gauge transformation acting on this then replaces Laplacian lambda with minus divergence of A. And so this thing, this changes that to e to the minus I alpha over 2 integral A0 dot plus del dot A squared d4x. And now when you put that in, what happens is these terms combine in the interaction with these nice gauge invariant terms and louse up the gauge invariance so that you now have a gauge fixing term. And so what you have is your new action is an integral minus a quarter FAB minus alpha over 2 dBAB squared plus ADJB plus any matter terms d4th x. So this is called a gauge fixing term. And the advantage here is that we've gone from a Coulomb gauge fixing term, which is awkward, to a Lorentz invariant gauge fixing term. And with the Lorentz invariant gauge fixing term, one can show that now, the upshot here is that now this omega time-ordered product of the gauge invariant operators, omega, is now an integral of the operators e to the I s alpha dA d psi over e to the I s alpha dA d psi. And one finds that the time-ordered product of a nu of x, a nu y, is the standard minus I delta thing that we learned about last semester, which is minus I integral eta mu nu over q squared minus I epsilon e to the I q x minus y d4th q over 2 pi to the 4. Okay. So that ends that discussion. Now, in the way most people do the analog, let us say, of the Coulomb gauge, the Coulomb gauge, which is awkward in QED, is very awkward in non-abelian gauge theory. And so what happens is, if we have a non-abelian theory, where, let me just write up here, the action is integral minus a quarter F. Let's see, I switched to Greek. A mu nu, F A mu nu, minus psi bar, gamma mu d mu, plus m psi, d4 x. Here F A mu nu is d mu, a mu, d mu, a nu minus d mu, a mu, and then plus g f abc, a d mu, a c nu, and of course d mu psi is d mu psi minus ig ta a mu psi, and so the T's are matrices generators of the Lie group that have the same. If psi is an n vector, then this is an n by n representation. What one does here is typically Weinberg explains in his volume 2, pages 14 to 18, he shows that the time-ordered product of gauge invariant operators is the O's and e to the I s, and now it's a delta function of AA3. This is called axial gauge, and then we have dA d psi over e to the I s delta AA3 dA d psi. And now the trick is, I think I'm going to cut this short. It's in the book, section 20.14. This is called the Fadeev-Popov tricks.
So the delta A3, this is like enforcing axial gauge, is that what that is? Or?
This is axial gauge,
Yeah,
right?
okay.
Setting A3 equals 0.
Yeah.
And well, let me put in a little bit of it. One useful equation is that the change of a gauge field under an infinitesimal gauge transformation is minus d mu lambda a minus g fabc ab mu lambda c. That's a nice equation. And what you need here, though, is to keep a track of the gauge of the Jacobian of, well, all right, let me just do it really. All right, let's just say what it is that we're doing. So I'm going to short circuit this, but let me just say you have O's, you have an e to the IS, and then there's this B of G, J, dA d psi, integral e to the IS, B of G, J, dA d psi. Now this J is actually a Jacobian, it's not a current. And B of G, what's B of G? First of all, what's G? Did I say what G? Well, no, all right. B of G is some function of the gauge fixing term. For example, this could be a product over all space-time and overall gauge indices. A would go from 1 to 3 for SU2, 1 to 8 for SU3. Delta of GA of X. And for example, this could be XA delta A3A of X. So that would be the axial condition. So G would be this, B of G is that. Another possibility is B of G could be e to the I over 2 integral G of A squared d4 of x, for example, if we're using the gauge fixing term that was Lorentz invariant there, d mu a mu a of x squared d4 of x. So in other words, the axial gauge, although it's nicer than the Coulomb gauge, it's still not as nice as a Lorentz invariant gauge. And the point that Faddeev and Popov used path integrals to show that one could, in fact, rewrite this. One way to rewrite it is to say, well, we're just integrating overall gauge fields. So one way is to do that. So you can use the Faddeev-Popov tricks to imitate the QED case and say just integrate over everything. And as I said, that's what one does in lattice gauge theory. Or one can, as I said, put in a gauge fixing term like this, and then one gets a, I guess I didn't bother to write down what is the, maybe I did. I don't know. I think we'll stop with this here because it gets progressively more technical. So let me just see what the numbering scheme is. I had a vector 2, 3. Okay. So the next point is I wanted to say a little bit about anomalies. This one. Yeah, this erases nicely if everything is dry. So what I want to illustrate here is the simplest case, of course. So let's just consider a free Dirac field, and so let's just first write minus psi bar d slash plus n psi. So this is the Dirac action. And remember, in Weinberg's notation, beta is, by the way, beta is this very nice matrix, 0, 1, 1, 0. So there are no i's, no minus signs. It's just an identity that's sort of cross-eyed. So beta, gamma mu dagger beta is minus gamma mu. So that's proper. That's how the gamma matrices work in Weinberg's notation. The Dirac equation is d slash plus m psi equals 0, and so in particular d slash psi is minus m psi. So now we can consider a current J mu, which is psi bar gamma mu psi. And as you might expect, this current has no divergence, and the way we see that is this is d mu psi bar gamma mu psi, and the other term is psi bar d slash psi. But d slash psi is minus m psi. So this is d slash psi bar gamma mu psi minus m psi bar psi. Well, if you compute this, use this, you can show that this is just m psi bar psi minus m psi bar psi, so that's 0. Now you can consider another case, namely the axial current, which is J5 mu, and this is psi bar, and where did I put the gamma 5? Doesn't matter. I wrote it this way. So this is psi bar gamma mu, gamma 5 psi. Remember, gamma 5 is used with everything. It's kind of it's like a fifth, and gamma 5 squared is 1. It's like a fifth spatial gamma, or fourth spatial gamma. And what you can show is that d mu J5 mu is 2m psi bar gamma 5 psi, which of course is not equal to 0. So this is called the axial current, axial vector current. It's conserved if the mass is 0, but not otherwise. All right, so let me see what I'm going to say now about it.
Does it correspond to like any physical current?
Give me that again.
Does it correspond to some physical current?
Well,
like what does it mean physically?
Well, what should I say? The weak interactions say, right? In fact, the way one used to think about the weak interactions before Glashow, Weinberg, and Salam was that it was a vector current, or in fact, that it was a vector current minus an axial vector current. And in those days, one just had a Fermi constant. I guess it was called GF, and then you had psi bar gamma mu 1 minus gamma 5 psi, and then you had the same structure repeated. Psi bar gamma, let's say gamma lower mu 1 minus gamma 5, or it might be plus gamma 5, depending on the notation. Anyway, it's whatever projects out the left-handed fields. And in the old Fermi theory, then, this might be an electron, and this might be a neutrino, and this might be a proton, this might be a neutron. I may have this. That's the way people thought of it in those days. So this would be your beta decay Lagrangian. And so you see this is if you leave out the gamma 5, you have a J mu, and you put in the gamma 5, take out the 1, you have a J5 mu. In any event, there's actually a funny story associated with this. I wish I knew more of the details, but a certain person who, I'm terrible with names, you know, he went on to win a Nobel Prize in experimental high energy physics, but he started out at Columbia as a theory graduate student, and I guess T.D. Lee gave him as a thesis problem, working out basically this time-ordered product of 3 currents, J5 lambda, say 0, J mu x1, j nu, x2. And where these j's are the j's that I wrote down there. And the problem with this is, as you know, when you have fermions, the fermion propagator is 1 over p, not 1 over p squared. So as soon as you switch from bosons to fermions, you've got a certain divergence that comes creeping into the S matrix elements. And so in particular, this thing was called the triangle diagram. And what you had was a gamma nu there, a gamma mu here, and a gamma lambda, gamma 5 there, and you basically have 3 fermion propagators, P minus Q, P minus K1, and then there's another term which sort of looks like this, gamma lambda, gamma 5, P minus Q, P, gamma nu, P minus K2, gamma mu. Well, it might have been Steinberger. Does that sound familiar? Anyway, these things are quadratically divergent, these integrals. And what you can do is you can, if you...
So is this a disconnected diagram, or are these 2 separate diagrams?
2 separate diagrams.
2 separate diagrams?
Yeah. It's bad enough. There's 2 separate diagrams than 1 diagram.
Okay. Yeah. But there's 6 sides in this time-ordered product.
So in other words, you have, all right, here, let me write it down. It's something like this, D4P. I'm following Z's book here. By the way, let me just say something. Z's books are very good. And in fact, the ideal way to learn theoretical physics, at least of quantum field theory and general relativity, is to use Z's books and Weinberg's books. So Weinberg gives you the deep fundamental underlying structure, and Z gives you presents the subject with its most approachable features evident, and then lets you plow on to more difficult things if you want to. So this is something like this, 2 pi to the 4th. There's a trace, and there's a gamma lambda, gamma 5, or 1 over p slash minus q slash. We're not going to compute this, but and this, I think, is the sum of the 2 diagrams. And what you can see is you have d4p there, p squared in the denominator, so it's quadratically divergent. And but the funny thing is that if you take one of these integrals and shift the p one way, and you shift p in the other one differently in the second integral, you can get the 2 to cancel, and you can say, well, the whole thing is 0. This is actually k1 mu delta lambda mu nu of k1 and k2. Anyway, so you've got something that, of course, the thing is you're not allowed to shift. See, over there I was saying you could shift the gauge transformation just like making a translation, no problem. Well, sometimes you can't make translations, and this is an example because it's a quadratically divergent integral. It turns out that if the integral is logarithmically divergent, you can get away with the shift, but not if it's quadratically divergent. And anyway, Steinberger found that his conclusion, well, if it was Steinberger, I don't know what the first name was, but anyway, he decided this is theoretical physics, and these confusing things where you don't know what you're doing, and you've got these quadratic divergences. Nothing makes sense. I'm going into experiment, and then he went into experiment, and 20 years later won the Nobel Prize. And now so this is one description of an anomaly, and notice there weren't any masses, there weren't any fermion masses here. That's because I was talking about the m equals 0 currents. In the m equals 0, both currents are conserved. When the mass is finite, only the vector current is conserved. And so the fact that, well, the attitude that people have toward this is to make a translation that will conserve the vector current but not the axial vector current. And that's the accepted interpretation of this. But a better point of view is the one that comes out of path integrals, and that was something worked out by Fujikawa. And what he was showing was that these two currents, the vector current and the axial vector current, are not on the same footing, whether the mass is 0 or m. Namely, that if you make you see the symmetry here, where is the symmetry that I wrote down? I guess I must have erased it. The symmetry of this current is associated with this transformation, and this other current is associated with e to the I theta gamma phi. And what Fujikawa showed was that if you set up the path integral and make a transformation on the fermion fields, it's a U1 transformation, everything's fine. But if on the other hand you do an e to the I theta gamma phi transformation, then the d psi part of the measure of the fermions in the path integral isn't invariant. So that's what I should, that's a way of saying it. All right, I'm going to leave that there. Let me just say something about nonabelian gauge fields, which I should have said earlier. Or maybe you guys had it in your seminars. You guys have the form approach to another. All right, let me just write it down. You can define a D as D plus A. This is the, what do you call it? The
exterior derivative?
Thank you. The exterior derivative, and this is a one form of the gauge field. And the nice thing is that d squared turns out to be dA plus a squared, and this is another expression for F, the Faraday 2 form. You guys had that in your seminar? Okay,
Yeah,
all right. Okay, so I'll skip that. 3 minutes for vortices, monopoles, and instantons.
Let's do it.
Wait, sorry,
Okay,
can I just ask real quick, what's the physical significance of this anomaly? Does it like tell us something interesting about physics, or is there some? Or is it just
Okay,
something
the
that
best,
everybody
the best discussion of that is, instead of me trying to just read this, you should read it slowly. So go to Z's book. You know, he has these books
Yeah.
in a nutshell.
Yeah.
This is quantum field theory in a
Yeah.
nutshell. It's chapter 4, section 7, and it's consequences of the anomaly. And he lists
Okay.
11 consequences of the anomaly. And in particular, all right, let me give you one consequence of the anomaly that's just related to the NUPAC seminar, particle astrophysics seminar that we had on Tuesday. One of the nonabelian axial anomaly suggests that the dipole moment of the electric dipole moment of the neutron should be much bigger than it is. And experiment shows that it's very small. One solution to that problem was a mechanism invented by Peche and Quinn, and then Weinberg showed that the Peche-Quinn mechanism wouldn't work unless you added in an axion. So since then, people have thought axions are really cool, and so they're looking at them. I've been a little bit dubious about axions, because notice that what you've got is, you've got an anomaly. Okay, this anomaly may affect the electric dipole moment of the neutron, and possibly the electron, and so forth. And so this is really a problem. But who knows what the solution is? The solution may be Peche-Quinn, maybe something else. In fact, I wrote a paper on something else. We'll check with the referee. Anyway, it could be various explanations that we haven't yet figured out that explain away why the neutron dipole moment is still small, despite the anomaly. On the other hand, it may be that it's the Quinn-Peche mechanism, and if it is, you probably need axions. But you know, the axions are removed from being, you know, a structural part of the theory by 1 or 2 steps, and so I think that could well not be axions. And so far, we've had 40 years of searching for them, and one found 0 axions. But of course, they could be very light, and they may even be transparent matter, which is also called dark matter. By the way, there's a cybersecurity firm called Dark Matter, which has the most pretentious and obnoxious commercials on Bloomberg. Drives me crazy, and moreover, the volume is too high. Well, all right, so let me give you I'll have to go over to say something about monopoles, vortices, and axions. The basic idea is that you've got some scalar field, typically, or set of scalar fields, and you've got some sort of potential like a Higgs field. So you've got something like phi squared minus, let us say, a squared squared. And this phi could be a single field, it could be a 3-vector, it could be an n-vector. And so what do you need? Well, you need that phi squared is a squared almost everywhere if you want to find that energy configuration. But now, as you go out to infinity, one solution is you say phi squared is a squared period, and it never changes from that value. In other words, phi 1 squared is a squared, phi k not equal to 1 squared is 0. Okay. You keep it fixed like that, no problem, energy typically 0 apart from quantum fluctuations. The other possibility is you say, we can have phi be some vector, and we can say that as it goes out to infinity, it always has length x squared, a squared, but it's pointing in different directions. Well, at first that looks great, but then you realize you've got a kinetic term to worry about, and the kinetic term diverges, I don't know, logarithmically or something. On the other hand, you gauge the thing. So your kinetic term then is d phi squared. And now the gauge field cancels the ordinary derivative of phi as you go out to infinity. So that means your gauge field has a certain behavior as you go out to infinity. So now what you've got is a map from the group, which is the set of gauge transformations, into space at infinity. And depending on what sort of space you're talking about, you could be talking about two-dimensional space, in which case it's a circle. You could be talking about three-dimensional space, in which case it's the surface of a two-sphere. Or you could be talking about Euclidean space, and you want something that has finite Euclidean action, in which case you are talking about the three-sphere at infinity. So you're going into Sn. So you have maps from the group into Sn, and these maps are then called the homotopy groups. This is pi n of g. And so, for example, the simplest case is into S2, e to the I n theta is a map from U1 to the unit circle S1, and obviously the group is Z, is pi 1 of what, S1 I guess. And then pi 2 of S2 is Z, and pi 3 of S3 is Z. Anyway, the people worked out all these homotopy groups. And so if you're talking about Euclidean four space, these maps are called instantons, and I don't know, I think the first ones were discovered by a Vogt, who also, if you're in 3 dimensions, one example is the monopole, the magnetic monopole, and in 2 dimensions, abelian Higgs vortex. Anyway, good catch.
Okay, good.
Yeah, you can stop.